All right, so I'm going to jump right in here. So thank you all for coming and attending. The theme of my dissertation work has been on visual methods to support automation of underwater manipulation vehicles. There we go. All right. So a large portion of my project was funded by a NASA P-STAR grant. And the P-STAR program funds terrestrial-based research that has applications in future space exploration missions. This work was largely a collaboration with several different research institutes, which are shown on the right of the slide. In recent years, the attention of the science community has been drawn to some of the liquid ocean-containing moons in our solar system. So one of these is Europa, which is a moon of Jupiter. And it's thought to be a viable target for extant life. This is because there's strong evidence that beneath the ice crust could be a liquid ocean. And in the core of Europa, there could operate similar geothermic processes that operate in the core of Earth. And this could lead to hydrothermal venting. This is really interesting because hydrothermal venting was one of the great discoveries of the 20th century. These venting systems were discovered to host chemoautotrophic organisms, that's what they're called, which can use chemical processes to get energy rather than photosynthesis. And these organisms in turn support tiers of exotic life. The discovery of thermal vents transformed the scientific community's view of the benthic ocean, which was historically thought to be a barren landscape, to now we know that it's a rich place for life. Also shown on the bottom right of the slide is what were dubbed Callisti limnes. These were discovered by one of my collaborators in 2012. They're carbon dioxide accumulating subsea pools, and they have essentially the same composition as opal in liquid form. And they were found to support colonies of silica-based organisms. So sub-ocean discoveries like these have really vitalized ocean research, and they motivate the exploration of environments where photosynthetic life is not viable. Within the P-STAR project, I led work towards automating underwater manipulation. In the context of a Europa exploration mission, an exploration vehicle must be capable of fully autonomous sample collection. This is because of communication delays to reach Europa, as well as high radiation levels, would make any kind of teleoperation practically inviable. And if you were to send a vehicle down beneath the ice crust, then communication becomes even more limited. Also, looking closer to home, terrestrial-based exploration of the deep ocean is currently extremely expensive. It requires a support vessel. You need a team of operators that are expert in operating the vehicle. So automation would significantly reduce the cost for exploration of our deep oceans. So this video shows an example of what a pilot-controlled push core looks like with an ROV. Our goal in this project was to kind of demonstrate this level of pick-and-place task, but without a pilot directly controlling the manipulator, using some automated methods. However, the underwater environment presents many unique challenges to automation. So one of these challenges is the limitation of vision-based sensors. And this is due to water column effects. So if you have really clear water and ideal lighting, which is shown at the top, you can get visual methods that work really well, which is shown by the dense point clouds. But in less than ideal water quality, where there might be haze and backscatter in the water column and the lighting is suboptimal, you tend to get vision methods that perform poorly. So this is just a brief summary of my research contributions that I'm going to go through in this talk. The first part of my work, which are the first 2 points, address the problem of detecting the pose of underwater tools so that they could be grasped and manipulated in an automated system. The envisioned application was to use a camera mounted on the wrist of the manipulator, which could be moved around to detect the tools and grasp them. I also collected and published an annotated underwater dataset that supported my work on the development of these visual methods. And then my latest contribution was the development of a SLAM method that's designed for underwater manipulation systems and can support real-time 3D scene reconstruction. My other contributions relate to the design and implementation of an automation framework for these underwater manipulator vehicles. So I'm going to go into my first contribution, which was SilhoNet. This is a novel method for object pose estimation from monocular images. Object pose estimation is broadly an important problem in robotics. My particular motivation was in marine applications, but this slide also shows some other domains where this is very applicable. And pose estimation is an extremely challenging problem. These images are from a popular inner benchmark data set, which shows some of the visual challenges of pose estimation. So you can have a variety of objects. There can be occlusions, objects can self-occlude, or there can be clutter in the scene. There can be varying scene illumination, and also objects appear different depending on what viewpoint you're looking at them. Also, while there's many applications which motivate the use of monocular images, the best performing pose estimation methods tend to use depth data. But I'm motivated by marine applications where depth sensors tend to be noisy or unreliable. Also, I'm targeting mounting a sensor on a manipulator. Housing a depth sensor on a manipulator would be very bulky to actually mount. So SilhoNet was inspired from a prior method that achieved state-of-the-art results at the time called PoseCNN. And SilhoNet shares the same feature extraction stage, but it also has a branching architecture. But I use a very different strategy for predicting the pose following the feature extraction. So here's a summary of the contributions made in the SilhoNet work, and I'll discuss this over the next slides. So here's a simplified diagram that shows the key novelty of SilhoNet. So I use an intermediate silhouette prediction, and the network predicts both an unoccluded silhouette and an occluded silhouette. The unoccluded silhouette is passed to a second stage network, which then predicts the orientation of the object. The translation of the object is predicted on a parallel branch to the silhouette predictions. SilhoNet runs on top of an object detection method, which gives region of interest proposals as well as the associated class ID for the detected object. And then as an auxiliary input on the bottom left, I create a rendered viewpoint of multiple views of the object model. And this is passed into the network to produce or to boost the performance. So here's a full diagram of the SilhoNet architecture, and I won't talk through all the details unless there's specific questions for sake of time. So I compared SilhoNet performance to other methods using an in their kind of standard benchmark data set called the YCB video data set. So here's the overall performance comparison of the pose predictions. This is using a symmetry agnostic average distance metric that was introduced with the PoseCNN paper. I also compare against the published results of another recent RGB method, MCN, which also uses multiple viewpoints to improve the network prediction, which is on the end MCN5, which uses 5 different viewpoints in their prediction. So SilhoNet and ground truth, with ground truth region of interest as input, which is the second column, performs significantly better than either of these competing methods. And then the third column shows SilhoNet performance when I use predicted region of interest as input from just an off-the-shelf faster RCNN network. And SilhoNet still achieved better performance than either methods when they're using a single RGB image and is on par with the performance of the multi-view network. All right, so I'm going to go into my second contribution, and this I dubbed SilhoNet-Fisheye, which adapts region of interest-based object pose estimation networks to work on fisheye and omnidirectional images. So this is a general framework that can be used with any kind of network that uses this strategy. Fisheye cameras have been gaining more popularity in robotics. This is due to their large field of view compared to their perspective counterparts. So these images illustrate that even a relatively wide 90-degree field of view perspective image captures significantly less information about the scene compared to the 180-degree field of view fisheye image shown on the left. However, extreme distortions in the fisheye image and omnidirectional images significantly reduce the performance of a network if you were just to process these images directly through without considering the distortion. So while attention has been given to problems of object detection in full fisheye images, there had been little work done on object pose estimation. which is particularly challenging in the presence of these distortions. And this is illustrated on the bottom right, where there's a large ambiguity when you're dealing with wide field of view cameras. So the T handle in this image is the orientation relative to the camera frame is the same, but just by translating it back and forth, you get a very wide ambiguity of viewpoints. So previous methods of dealing with omnidirectional distortions can be roughly categorized under 3 approaches. So the first approach is generating multiple perspective projections from a sphere, such as a cube map, and processing each projection separately through the network. The second approach is adapting the kernel sample locations based on a spherical distortion model or a learned mapping. And then the third common approach is resampling the spherical image based on a uniform sampling geometry or graph, and then processing the spherical representation with specialized convolutions or in the spectral domain. But methods like the cube map that operate on multiple perspective projections suffer from feature discontinuity at the border. And then methods that operate on a graph generally do not scale efficiently and are typically rotation invariant in the convolutional space, which is not desirable for pose estimation. So most closely related to my work are the methods that resample the convolutional filters based on a distortion mapping, but these methods have not been demonstrated for the problem of object pose estimation. So here's a summary of my contributions in this work, which I'll talk through on these slides. So in this work, I assume a fisheye camera that follows the equidistant projection model, which is the most common projection model for fisheye cameras. Though my method generalizes to any projection model that can be mapped to a sphere. And then to deal with the visual ambiguity induced by the distortions, I first formulate a mapping of the image pixels to the unit sphere, as well as the inverse mapping. I then define the apparent viewpoint as the mnemonic projection from the sphere onto the object-centered tangent plane. The orientation of the object is regressed relative to this apparent viewpoint. And then a rotation correction can be applied to recover the true orientation relative to the spherical coordinate system. So given a spherical mapping or a spherical mapped image with the sphere coordinate system coincident with the fisheye camera frame, and then an object in the scene with rotation and translation given relative to that spherical coordinate system, the apparent viewpoint is described by a virtual perspective camera with the optical axis rotated to intersect the center of the object. The intersection of the virtual optical axis with the sphere in polar coordinates can be calculated from the object translation. And then a rotation adjustment matrix can be constructed from the coordinates of this virtual axis intersection point. The orientation of the object is then regressed relative to this virtual optical axis, and the true orientation can be recovered using the rotation adjustment matrix. This framework assumes that the translation and orientation are regressed independently of each other, which is typical in pose estimation networks, and the regressed translation is then used to recover the true orientation. So I compared 3 different variants of the SilhoNet network adapted for processing full fisheye images, and all variants regress the apparent viewpoint. So the first variant is the baseline method, where I just process the images through the vanilla SilhoNet network without considering any kind of distortion compensation. The second, projected variant, I first process the images through the feature extraction stage, and then I project those features onto the sphere. And then a region of interest is cropped from those features and projected through the mnemonic projection to a tangent plane, and then processed through the rest of the network. And then the third, on the bottom, perspective method, what I call it, projects a region of the fisheye image onto a virtual perspective image centered on a region of interest. And then this virtual image is processed through the entire network pipeline. So as a further comparison point, I also replaced the silhouette prediction branch that has the secondary network to predict orientation with just a direct prediction of the quaternion orientation vector, rather than going through the silhouette in the second stage network. So I refer to those methods as a direct version of each variant. When I was doing this work, I found that there's a lack of publicly available annotated fisheye data sets for pose estimation. And most related prior works that dealt with fisheye images either resorted to creating custom data sets through simulation or collecting small scale data sets in a lab. So I addressed this issue by collecting an annotated fisheye data set for object pose estimation, with a further novelty that this data set was collected in natural deep ocean environments. And there's a lack of annotated images in general for underwater data. So when collecting this data set, I used April tags to provide consistent ground truth poses of the camera and the image sequences, which is illustrated in this slide. So the April tag-based SLAM was used to produce globally consistent camera poses for each frame, and then object models were fit into the sequence to automatically produce the annotations. An observation in underwater manipulation is that each institution tends to use the same kind of handle for all of their different tools that they use. So this can benefit automation, because if you can just detect the pose of a tool and you can model the attached, detect the pose of a handle and then model the attached tool, then you only need a method that can automatically detect the tool, or the handle, sorry, backwards. So towards this end, our collected data set has annotated poses for 3 different types of common handles used in underwater manipulation. There we go. Just had to restart. All right. There we go. So yeah, so this shows April tag detection SLAM just running in ROS, and the output is a consistent camera pose for each image in the sequence. So I also couldn't find a freely available tool to do the kind of annotation that I wanted to do on this data set. So I developed my own tool, which enables projecting the object models into the sequence. You can scan back and forth in the sequence, tweak their fit, filter out outliers, and then project the whole image sequence. So these are actually fisheye images, but they're center rectified for visualization of the projected models.
Why do you have tweak tags? This is redundancy.
Yeah, so how we did the tags are kind of meaningless, like it's arbitrary where they're placed. We just put small tags on the tools because we'd be getting close to them. And so having small tags kind of let you get arbitrarily close or far. And then we put big tag plates that kind of dispersed out in the scene. But in this data set, the actual tags don't really matter. We found that 3 tags was more robust to detect than 1 single tag, which could be noisy in the fisheye and in underwater. So the more tags was just greater robustness. So this table shows the translation prediction accuracy for the 3 different network variants, where a higher percentage under a lower threshold error means better accuracy. So if you consider the first column, which is the 5 centimeter error column, the perspective variant significantly outperforms the baseline, while the projected variant shows some improvement. All of the direct methods on the bottom show a significant degradation in performance compared to the methods that use the intermediate silhouette for the orientation prediction. So this indicates that even though silhouettes are not directly used in the translation prediction, they still guide the network training to learn some kind of scaling of the features. Then this table shows the orientation prediction accuracy. So again, the perspective variants outperform the baseline by a significant margin, and the projected variant does not perform as well. But the direct variants in this case perform better than the methods that use the intermediate silhouette. And I believe this is because in this data set, I only trained on the collected data set and didn't use any supplemental kind of rendered viewpoints like I did in the benchmark data set for the YCD video data set in the original SilhoNet network. So I believe that these results could be improved by supplementing the training with simulated data. But the important point is the comparison between the different networks. And then this kind of supports that view. So here I visualize the predictions of the perspective variant, which was the best overall performing on the sample sequence from the test sets. And it's evident that the silhouette predictions, they're like you can see they kind of match, but they do have a lot of noise and distortions. So this could improve with supplemental training on simulated data. All right, so next I'm going to talk about my next contribution, which addresses the problem of designing underwater optical systems. I'm not going to spend a lot of time on this one for sake of time, but I'll just briefly go over it. So the motivation was that designing underwater systems is a complex task. So there's a big design space. You have to choose your sensor, your lens, your lighting. And if you're coming in this without a lot of field knowledge, it could be a complex problem. And then the specifications of each individual component can greatly affect the performance of your imaging system. So the process of designing and tuning such systems is often labor intensive, where you kind of tune your parameters, and you go in the field, you check the performance, make sure your noise levels are reasonable, make sure your image quality is good, and then you kind of go back and forth until you're at a happy medium. So myself and my lab mate at the time, Eduardo Iscar, we developed an open source tool that kind of took all of this in-house knowledge and fieldwork knowledge, and we developed a simplified model incorporated in this tool that can kind of give you a back of the envelope calculator for how to design these kind of imaging and lighting systems. They inform the initial design choices, and you can tune parameters to see how they affect the overall performance. Our model accounts for light spectrum attenuation by the light in the water column, benthic reflection, and lensing and sensor effects. And then we experimentally verified the performance of our model in a simple lab tank setup where we had a clear acrylic tank. We put a strobe and a light on one side of the tank, and then a white kind of matte board inside the tank on the opposite wall. And we used a spectrometer to measure the light signal at the board and at the cameras. And then we verified that the predicted attenuated light signal matched what we measured with the spectrometer. And then we did measured responses for 2 different camera sensors, where we kept the scene lighting constant, but increased the sensor exposure time, and verified that the response curves matched up with the model. And then we did a similar test, but kept the sensor the same and changed out the lens, and then changed the aperture values, and also verified that we had a reasonable approximation. This is just a screenshot of the tool. It's just a similar, simple calculator kind of interface. All right, so I'm going to move on to my next contribution.
Wait, that's a simple calculator?
Yeah. Well, hopefully, like, there's a paper that goes with it. So if you read the paper and then use this, hopefully it can kind of guide you into first steps towards designing a new camera system for underwater.
What would you change about it if you want to do it again?
So there's definitely some future features that we'd like to add. So right now, this is kind of designed for survey vehicles that are looking straight down. So say, an Ivor type vehicle or something where your strobe is shining straight down, your camera is looking straight down, and you're assuming like kind of a diffuse benthic scatter from that. So it would be cool to have a system that can model multiple lights coming from different angles, and how those would physically interact with the scene and with complex structure. And that could also be really useful for doing things like having a light on a manipulator and being able to do real-time kind of planning to inform how to light your scene with that light. Things like that would be really cool. All right, so my most recent work was focused on developing a hybrid SLAM method for underwater vehicle manipulator systems. So this work is motivated by the need for automating underwater manipulator and sample collection missions would require a 3D reconstruction of the workspace that must be generated to inform a manipulation task. So current SLAM methods, where's my mouse? There it is. So current SLAM methods applied to underwater domain generally fall within 2 categories. So the first case is generating large-scale dense reconstructions from image surveys. These methods are computationally intensive, and reconstructions are generally processed offline. And then the second use case is for terrain-aided vehicle navigation, which operates in real time, but they construct only a very sparse feature map, if any. But little work has been done on real-time reconstruction methods that are aimed towards automated manipulation and direct interaction with the environment. However, direct interaction with the seafloor environment comes with risks, in contrast to systems that are just making passive surveys of the seafloor. So one of these challenges is that once a vehicle commits to a particular sampling location, it's not always feasible to move the vehicle around because you could greatly disturb the scene state, and you'd have to wait for the water clarity to equalize out. And often then the view of the workspace is limited to kind of one view for vehicle mounted cameras throughout the duration of the sampling procedure. So a natural solution to this problem is the fusion of multiple imaging sensors into the reconstruction framework. However, space for additional cameras on underwater vehicles tends to be really constrained because you have a lot of things mounted on the vehicle. So in my work, I have used a hybrid camera system that's composed of a vehicle-mounted stereo pair and then a manipulator-mounted wrist camera that is a fisheye. And the stereo camera can provide dense point clouds of the scene, but only a limited view of the manipulator workspace. The fisheye camera, on the other hand, can be moved around actively throughout the scene to obtain different perspective and provide a super view of the environment. So this motivates the SLAM method that I worked on, which fuses the wrist-mounted fisheye camera with the vehicle-mounted stereo to extend the reconstruction outside of that limited stereo view. And it can also fill in shadowed areas in the scene structure. So one relevant prior method that inspired my work is called PostSlam, where cameras mounted on different agents were synchronized and processed within the same mapping framework. The key differences are my use of stereo features, which constrain the map scale, the fusion of independent hybrid camera frames into the same map, and then the specific adaptations of the method to work in the underwater environment. So here's an overview again of my contributions, but I'll just go through these in the slides that follow. So when I collected the images for the previous data set that I showed, the fisheye data set for my silo network, I also at the same time collected synchronized stereo images with those fisheye data. So I processed 4 unique hybrid image sequences from that data set for evaluation of the hybrid SLAM method. Less stereo images from these sequences are shown here. And I used the same April tag kind of SLAM processing to get ground truth poses of the stereo and fisheye images in these sequences. However, in these hybrid sequences, the stereo is pretty much stationary because the ROV is kind of set down on the seafloor. So I wanted to have a stereo data set that could really evaluate the underlying stereo SLAM performance of the method. So we used a diver operated stereo rig, which I helped build, to collect an image survey of a coral reef in Australia. So I processed that stereo image data set with ColMap to produce ground truth trajectory. And then I started by approaching the development of my method from the ground up. So the first question I wanted to ask is, what is the best feature to use in the SLAM method? So I wanted to find a feature that was suitable to the underwater environment and also could robustly match between the hybrid frames, being a fisheye and a perspective stereo. So I evaluated the feature matching performance of different features by estimating an essential matrix using feature matches across hybrid image pairs. I initially found that many features were located on the artificial April tags in these data sets, which skewed the results. So I projected masks over the tags to limit the evaluation to natural features. Then I compared several popular conventional features as well as 2 deep learning-based features, which were context desk and superpoint. Since the essential matrix does not provide scale, I evaluated the translation accuracy by using the angular difference between the translation vector direction of the predicted and the ground truth. I used area under the accuracy curve as my evaluation metric. So interestingly, context desk greatly outperformed all the other features. If you look at the mean number of feature inlier matches per hybrid frame, it's nearly double the best performing conventional feature, which is root-sift. Out of the conventional features, SIFT and its variant root-sift perform the best. So for my work, I chose to use a GPU accelerated SIFT feature for ease of implementation. But what's really interesting is context desk uses the SIFT feature point detection, but uses deep learning to describe the descriptor. So my method is directly compatible out of the box with context desk features. So my next step was to find or develop a visual odometer based on my chosen feature that performed well on underwater imagery. So I took inspiration from prior work on underwater stereo SLAM, which used the VisO2 odometer, which is a stereo odometer. So the high-level algorithm of VisO2 is outlined here, but I'll skim past this for sake of time. But just a couple notes. So the Sobel filter responses are just simple kind of edge blob filters that this method used for features. Stereo matches were matched by searching a window, projecting a window into each stereo view, and then circular filtering between the current stereo frame and the previous stereo frame, where you take a feature, You match it in the current left stereo image, the current right stereo image, the previous right image, the previous left image, and then back to the current left image. And if the same feature makes that whole loop, it's an inlier. And then they also used epipolar constraints on the stereo matching to filter results. And then they did a third step doing Delaunay triangulation of the inlier features to create a mesh. And then they filtered those neighboring features by requiring them to have a similar disparity to each other. And then they bucketed features to uniformly distribute them across the images. And then finally, they used a ransack method combined with Kalman filtering to estimate the motion with respect to the previous frame. But when I tested this on my stereo survey sequence, this was the best result I could get after extensive tuning. So I adapted this odometer to GPU accelerated SIFT features. So I used CUDA SIFT. And instead of searching stereo matches in a window, which the window needs to be fairly large because underwater images tend to be collected at low frame rates, I do brute force matching on the GPU, and then I keep the circular filtering and the epipolar constraint. I found that the outlier removal by the Delaunay triangulation was removed too many good features for underwater data. And I also found the same thing with the feature bucketing, because underwater features tend to be clumped together on sparse areas where there's good features. So if you try to bucket and filter, you lose a lot of features. So overall, I found that the circular matching and epipolar filtering produced a high percentage of inliers, which was good enough for the ransack and based ego motion estimation. So here's a top-down view of my modified odometer results on the stereo data set, showing very good estimates in the XY plane. However, there was a consistent drift of the odometer in Z depth estimate. So my next step was to develop a full SLAM method. So I based my method on OrbSLAM 2, which is a very popular and mature SLAM method for both stereo and monocular cameras. It uses a 4-threaded architecture for tracking, local mapping, loop closing, and then full bundle adjustment, which is a full optimization of that. But the implementation of OrbSLAM 2 is tightly integrated with Orb features, which was one of the features I tested and performs pretty poorly underwater. So here's a block diagram of my SLAM method. So for sake of time, I'm only going to mention some of the high-level notable differences from OrbSLAM 2. I modified the tracking thread heavily. So there are 2 separate branches for the stereo and monocular fisheye frames. CUDA SIFT features are extracted from each new frame and then propagated through the entire network pipeline. The stereo branch uses my modified VISO2 odometer instead of the velocity-based tracking method that's used in OrbSLAM 2. And the initial map is created from a stereo frame, which provides the initial scale constraint, after which both stereo and monocular keyframes can extend the map. The other threads in the system remain largely the same to OrbSLAM 2 with some modifications to support the hybrid keyframes. I also adapted the bag of words-based visual place recognizer used by OrbSLAM 2 to use SIFT features. And I trained it on a 1,000,000-word vocabulary with a diverse set of underwater images. So here's my SLAM method, just stereo performance on the stereo survey data set. So I note here that I did test OrbSLAM 2 off the shelf. It failed to track after a couple frames and could not recover. I also did a test where instead of using my odometer, I used the velocity-based tracking method used in OrbSLAM 2 with the SIFT features, and it still lost track after a couple frames and could not recover. So the odometer is critical to the performance of the system. So here's the final map results from the full stereo SLAM system. So this is with both 4,000 features extracted per frame and 2,000 features. And you can see those interconnecting lines are dense loop closures with neighboring spiral lengths. So without loop closing shown on the left, there's still some Z drift in the full SLAM method, but not as much as just using a visual odometer. And this is because each frame is still optimized on a local window of keyframes in the map. And then with loop closing shown on the right, there's no Z drift. So here's the table that shows the accuracy with and without loop closing. Notably, when the number of extracted features is doubled, the number of map points also doubles. So this shows that the system scales well. The system also achieves greater than 10 hertz when 2,000 features per frame are used, and easily achieves 5 hertz for 4,000 features per frame, which 5 hertz was the rate that the data was collected. So here's the performance of the method on the hybrid image sequences, where both the stereo and fisheye are being fused into the map. The keyframes at the top of the map that look kind of stationary, that's the stereo, and then all the other keyframes lower down are the fisheye being fused into the map. So these are just some still frames that show a very different perspective with the fisheye relative to the stereo, and showing that the fisheye can extend the map and fuse effectively. So here's the overall translation error across all these hybrid sequences. The error is approximately 2 centimeters, and the overall orientation error is about a degree. So one of the tests I did is on the last 2 columns, I processed these sequences running in full hybrid mode with both the stereo and fisheye, and then using just stereo, so without the fisheye to extend the map. And when running in hybrid mode, the number of keyframes is approximately double, as well as the number of feature points. This also shows that the fisheye can effectively extend the map beyond the limited stereo view. Also in hybrid mode, the method achieves 3 hertz for 6,000 features per frame, which is the frame rate that the hybrid data was collected. So I have a few notes on future work for this. So one of my original intentions was to have a kinematic factor between the fisheye and the stereo through the manipulator, which would improve the system robustness and could also enable real-time feedback for manipulator calibration. I wasn't able to get this in this work, but it definitely would be interesting future work to pursue. Also, exploring deep learning-based features could improve the mapping performance, which I saw from my experiments. And then third, dense reconstruction stage should be added that could be optimized by the sparse feature map. And this would produce a fully formed 3D reconstruction method to support automated manipulation. All right, so I'm going to go into my final contribution. This relates to hardware and methods for automating underwater manipulation. And this is more field work oriented and demonstration type work. So the motivation for this is that, well, most terrestrial manipulators are electric, especially those intended for automation. Underwater manipulation systems used in the field are mostly hydraulic. In general, this is because hydraulic systems have a higher power to weight ratio over electrics and are capable of operating to greater depths. So this table shows a standard hydraulic manipulator in the middle, compared on the left to a similarly spec'd KUKA arm, which is a popular terrestrial-based manipulator system. And the arms have similar lift capacity and reach, but you'll notice the KUKA arm is much heavier and would not be appropriate to deploy on an underwater vehicle. Shown on the right is a very recently announced underwater manipulator that's electric, announced by Saab. And they were able to achieve really impressive specs with their manipulator. And it's designed to be kind of a drop-in replacement for standard industrial hydraulic arms. But if you look at the power requirements, it's nearly 2 orders of magnitude greater to operate the electric than it is the hydraulic. So this is an issue for vehicles that have to have all their power on board. So this is more designed for ROVs that get power supplied by a tether to a surface vessel, which essentially has unlimited power. But the actual vehicle that I used in a lot of my demonstrations does have all the power on board, and this would not be an appropriate manipulator.
So just for scale, the KUKA, that's like the big, like 15-foot KUKA?
No. They have several models. So I expect this one to be the same dimension. So you see the reach is 1.8 meters.
Yeah.
Yeah, so it's, I think they sit up about 3.5 feet high or so, 4 feet high maybe.
It's like 700 kilograms?
That's what their spec said.
Wow.
But I don't know if that includes like the mounting base or what.
The way you bolt in the floors.
Yeah. Which there is lighter arms, but then you have to seal them for underwater. And so Saab is really the first that's demonstrated an actual manipulator that looks like it could be viable for industrial operation. There's a lot of like research ones that people have demonstrated prototypes, but nothing has been robust enough to actually deploy. And these, again, are industrial scale ones that need to handle lots of weight. So hydraulic manipulators have several positive attributes, which makes them the manipulator of choice for deep ocean vehicles, but they're not designed for automation. They provide limited feedback and less precision compared to their electric counterparts. So further challenges of automating underwater manipulation compared to terrestrial systems is that the hardware and operations are much more expensive. The hardware is prone to failure, and you must anticipate failure in the field, which I experienced on basically every field trial that I was involved with. The observation of the system is limited, so when the vehicle is deployed, there's increased risk of operation and testing. Usually, you only have visual feedback from cameras and some sensor data. And then intervention is also limited if something goes badly. You don't have a fail-safe switch that you can just hit, and recovery of the vehicle is the priority when you're doing field work. So there's been several past projects focused on automating underwater manipulation, but many of these fall under the task of intervention on man-made structures, such as turning a valve, and most of these works also use electric manipulators in shallow water environments like pools. There was some very recent work out of the University of Limerick in Ireland, where they developed a visual servo control framework for hydraulic manipulators, and they demonstrated really impressive precision control of the manipulator in both tank and field deployments. But their system did not employ any kind of path planning, and they were really focused on just the precision task demonstration. So my work on manipulator autonomy is complementary to these prior works and emphasizes practical field demonstrations in natural seafloor environments. So in order to develop and test the automated system, we built an in-air test bed that uses the same type of hydraulic manipulator used in our field trials. The test bed also has the same machine vision camera setup and a similar configuration to how it will be mounted on an ROV. The vehicle mounted stereo cameras are kind of used for scene reconstruction and vehicle state estimation, which you've already seen some of that. And then the wrist-mounted fisheye camera is used primarily for the tool pose estimation and extending the 3D reconstruction. This slide just shows the calibration procedure that we went through for the visual and kinematic system. I won't really spend time on this. This slide shows the NUI ROV, which was my primary vehicle that I did fieldwork with. This is operated by Woods Hole Oceanographic Institute. So if you look on the top right, the vehicle uses a hair-thin fiber optic tether for communication only. And that's the only thing that connects it to the surface ship. That tether is coming out of a little hole in the middle of that canister. So I don't know if you can really see it in this image, but it's very tiny. So all the power has to be carried on board the vehicle. And if the tether breaks, the vehicle switches to an AUV mode and can autonomously return to the vessel. The vehicle is designed for operation under ice, so it can operate kilometers away from a surface vessel. Whereas most vehicles that have the standard tether, they have a very limited distance that they can operate from the ship. So one of the big automation challenges with the NUI vehicle was also these articulating doors. So because it can kind of be a hybrid AUV, ROV, these doors can open and close. And due to space limitations, I had to mount the stereo camera on the port side door, which you can see in the image, and then the manipulator was mounted on the starboard door. However, these doors were open and closed by hydraulic rams, which didn't have any kind of position feedback. So in order to project the stereo point clouds into the scene accurately and also plan safe motion paths, we had to come up with a way to estimate the door joint positions. So I again relied on April tags to build kind of a virtual door joint estimator using the stereo cameras. So this slide just kind of shows how that works. So I had tags on the chin of the vehicle and near the base of the arm, the stereo pair, do some trigonometry and can have essentially a virtual joint feedback. April tags were also attached to the tool handles, and the model of the mounts and the handles were directly modeled so that you could get the handle posed directly from the tool or from the fiducial detections. In order to make very transparent every step of the automation control, I developed a high-level interface to move it, which is a motion planning framework that's very popular in robotics. And this interface was geared towards ROV manipulation tasks. This enabled a pilot to step through a task and visualize each movement before execution so they could verify it looks safe. So this is just showing a simulated demonstration of how that interface works. So here's a block diagram of the system depicting how the autonomy system operates. The outer red flow lines depict what standard teleoperation looks like, where a pilot directly controls a manipulator and gets feedback from the camera systems. In our system, we take a shared autonomy approach where the pilot acts as the mission planner and sends high-level manipulation goals to the autonomy interface. So this is a conceptual diagram of the system components. I just want to point out here that besides the graphical interface to the autonomy, we also had a natural language interface, which is a prototype, where the pilot can simply speak a desired command. This was work done in collaboration with Matthew Walter at the at Toyota Technological Institute in Chicago. So I'll now go into some of the results we've gotten from the field. So I've participated in 4 research cruises over the course of my PhD work. The first cruise was with Schmidt Ocean Institute in the Hawaiian Channels. The second cruise was also with Schmidt, where we explored the Costa Rica continental shelf break. And then the third cruise was in the Mediterranean Sea off the coast of Santorini, where we explored the active submarine volcano Kolumbo. Both of these cruises and the cruise in Costa Rica were operated like analog missions to an extraterrestrial exploration of, say, an ice moon like Europa. In this analog, the surface ship operated like an orbiter doing flyby mapping. The gliders acted like long-range reconnaissance drones. They were outfitted with mass spectrometers to sense chemical anomalies, and they also had scanning sonar to do terrain-aided navigation. And then the ROV, the NUI ROV, acted like a lander, where mission waypoints were informed by data collected from both the ship and the gliders. So the first demonstration of my system was on the Costa Rica cruise, where we collected the data sets used throughout my thesis work. We mounted our camera system on the Sebastian ROV, operated by Schmidt, and we demonstrated 3D point cloud visualization and the calibrated kinematic configuration of their manipulator. And we were able to have this as visualization for the pilots in real time. Then the next demonstration was on the Atom testbed, where I showed fully autonomous execution of the pick and place pipeline using just the graphical interface and no direct pilot control of the manipulator. So I'll just let this finish here. This is essentially, before I was allowed to deploy the system on the actual vehicle, I had to do demonstrations in simulation and on the testbed to show that it was a viable method. All right, so during the cruise in Greece, exploring the Kolumbo Caldera, we made the first demonstrations of the full system in the field. And here we were able to control the manipulator through the interface to collect a slurp sample, which is that yellow tube kind of attached to the manipulator. That's essentially a giant vacuum, which can suck up bacterial samples. Due to issues with the hydraulic arm on this cruise, though, we weren't able to do a pick and place with a push cord. Also, as proof of concept on this cruise, we showed an initial demonstration of natural language control of the manipulator. So we had an NLP network, natural language network, that interfaced with the automation system, and it enabled voice and text actuation of the interface commands. In this video, we demonstrated commanding the arm to move to a target location, then back to stow with text commands. All right, and then finally, this last September, I participated in a cruise off the coast of California, where we demonstrated distributed shared autonomy for ROV manipulator control. My collaborators developed a Unity-based app which allowed users not physically present on the ship to interact with the autonomy system. The app visualized the vehicle state and the 3D environment and provided a command interface where a user given access permissions by the pilot could send requests through either a graphical interface or a natural language interface. A shore server communicated directly with the ship and distributed the sensor feeds to any number of connected users. My collaborators in this work included Andrea Danielle and Professor Matt Walter from Toyota Technological Institute, Annie Fung, who is a joint PhD or in a joint PhD program at MIT and Woods Hole Oceanographic Institution, and Dr. Richard Camilli, who is a scientist at Woods Hole. We demonstrated cooperative control of the manipulator to perform a complex sampling task with no pilot in the loop. So in this demonstration, myself and Matt Walter were on the ship, while the others interacted with the system through the app from various locations on the shore. So here is a highlight video of our demonstration. So Andrea used natural language to interface with the app to send a request to pick up an X-ray fluorometer tool that we carried on board. From the pilot interface, I verified the generated motion plan and then executed the requested task. After I used the pilot interface to grasp and remove the XRF from the tool tray, Amy Fung used a VR version of the app to position the tool in the desired sampling location. And then not shown in this video is that after the tool was placed, Rich, who was the one who designed the XRF tool, was able to monitor the placement of it from the app, give us feedback in real time, and he was also able to monitor a real-time feed of the sensor, because it's an active sensor, to determine when it had collected enough data. So all of this was able to be done in a collaborative manner with no pilot control manipulator at any point. So this was a super exciting demonstration because it showed how field robotics can be distributed to be more collaborative and inclusive. So no longer is it limited to participants that have to be physically present. So this kind of system also enables broad outreach and engagement where students and researchers can be plugged in the field deployments in real time. We also used the pilot interface on this cruise to demonstrate our target push core sample collection using only high-level commands. So this is just using the push button interface. I did cut out a couple pauses. And I think the video is sped up by like 2 times. And there's push core. Okay. So in conclusion, that is an overview of all my research work over the last 5 years. I want to thank all my lab mates with whom I've shared many experiences, my family who has offered endless support to me as I pursued my dreams, and then Matt, who saw something in me when I was fresh out of undergrad. So my work throughout my PhD has been motivated by a passion for discovery. We only have one planet, which so far is the only known source of life. Yet so much remains to be discovered on our own doorstep, cosmically speaking. So my hope is that the technologies that I'm working to develop will advance our capabilities and reduce the costs to explore and discover first the oceans in our own planet and eventually the oceans of other worlds. I believe discovery leads to understanding, and understanding informs how we can conserve our vital resources and preserve our rich habitats. The oceans are not a vast desert, but are full of diverse environments teeming with life in the most beautiful and exotic forms. And we are only beginning to understand how big a part these ecosystems play in the health of our planet and our future existence. Thank you.